We're now going to tackle part B, which is finding the maximum volume. Now, when we do our differential calculus unit later in the year, we'll be able to do it analytically, which means looking at the function and then performing some calculations to work out the maximum. But without that, we really do need to rely on our graphics display calculator in order to find the maximum volume. Now, just really briefly, before I show you how to use a graphics display calculator, what we have in front of us is we're going to be drawing a cubic graph. So we know that our cubic graph is going to be, we don't know where it's positioned, but it's either going to be like an inflection like this, or we know that it's going to go like a roller coaster like this. It could go backwards, so like that kind of thing. But nevertheless, we've got some definite shapes of our graph. Now, if we're looking for a maximum volume, then we're looking at the greatest height of this graph, because all of these graphs are going to be volume versus that base length x. So all of these will be volume, okay? And our calculator can help us determine what that maximum will be. Before we do that, let's have a think about what the actual graph is going to look like in terms of legitimate values. We sometimes call that a restricted domain, because when we have a look at the graph, we are going to have some constraints on what values are legitimate, just like we did when we were working out the possible values of x. We had to discount negative x values because x can't be negative, right? We can't have a negative base length. So if I'm drawing my graph legitimately this time, if I just sort of draw it like this, a bit off to the side, I should be using a ruler really. So I've got v versus x here. So we can automatically say x can't be negative, which means that I don't need to consider anything on the other side of the y-axis or the v-axis. Also, the volume can't be negative either. We can't have a negative volume, so that means this is out as well. So really, we're only interested in this space here. But we can go one step further, because if we consider the other dimension, which is h also can't be negative, right? It really has to be bigger than 0, but we can at least say 0 is kind of like the minimum tolerated value. So what does that mean in terms of the volume? Well, if h can't be 0, and I'll just zoom up so you can see what I'm talking about here, that means that if h is given by 160 minus 2x, and h has to be bigger than 0, that means x, or 2x, can't be anything more than 160, right? If it was 161, then the height would be negative. 160 still doesn't make sense. So we can sort of, but it's a kind of like the threshold. So we can sort of say, well, this means that 2x can be at most 160, which means that x can be at most 80. So if I go back to my graph now, I really only want to consider, I'll put a red dot here so you can sort of see it, where x equals 80. I don't want to consider anything beyond 80 either. So I can shade out anything beyond here as well. So even though we might have an x value over here, it'll give us a negative height, so it's not worth considering. So we're really just left with this tiny, tiny space in here. Okay, so that's just so we know what we're looking for, because if we know what we're aiming for in terms of this space here, it'll make better sense of our graphics display calculator when we use it. So I'm going to flip over to the GDC now. And I've just started off a little bit. I'm going to add a graph page, and I'm going to pop in our function that we had originally. So if I go back to this page here, we can see that the volume was given by this function here, x squared outside of 160 minus 2x, or 160x squared minus 2x cubed. Not the 50,000, because that was for a specific volume. It's v equals this. So that's what we're going to put into our calculator. Now you can put it in any form you want to. I think I'll put it in the format of x squared 160 minus x, like so. I'll flip back so you can confirm that. X squared 160 minus x, x squared 160 minus, 2x. So I'll pop my 2 back in here. And now I'm ready to graph it. So press enter, and there's my graph. But it's looking pretty dodgy, isn't it? The way it's been drawn. It's very squishy here. We can't really tell much from it. So we're going to have to do a bit of zooming out in order to see the graph in all its glory. And if you think about it, going back to these values here, you can see by looking at these dimensions here, I don't want anything the X dimensions specifically, I don't want anything too small, really. These axes go from -10 to 10. Well, I don't need any negatives at all, and I need to get as far as, at least as far as 80. If you remember, we looked at that on our graph here, that it's going to go from 0 to 80, and the volume is going to be pretty big as well. So I'm going to go to the menu button and I'm going to go to Windows Zoom. Now you'll see there's a whole bunch of options here for zooming, including zoom in and zoom out, which basically allows you to click, 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 click until it's zoomed out. I don't like using these because they can be a little bit random, whereas if you use Windows settings, you're being very deliberate about your zoom. So I can go to Windows settings here, and I'll leave it as at -10, but I'm going to go all the way to 80 on the X axis. And then for the Y axis, well, it's going to be in the thousands, isn't it, the volume? So let's go for a minimum of 1,000, and let's go up to 150,000. Just guessing the number, really, to see what happens. Click on OK. Well, that's pretty good. I didn't leave myself any wriggle room over here on the X-axis here, and I don't quite have the top of the graph here. So I'll go back to menu, go back to Windows Zoom, go back to Windows settings, and I'll just adjust those a little bit more. Again, this just gives me a lot more control over what I'm doing rather than just using the zoom in, zoom out. So I'll make it 160,000, like so. Click on OK. Now I've got the graph nicely represented with a little bit of wriggle room either side. So we've got our 80 there, we've got our 0 here, and this graph is all the way through here. Okay, so we can see that clearly that there's a maximum up here. If the graph had sort of gone like this, and then like this, and then up like this, then the maximum might be at x equals 80. So we just got to be careful that we take the overall broad domain from 0 to 90 and look for the maximum value over the entire thing, not just the turning point, but over the entire thing. But for this function, it looks like it is basically that turning point there. So let's work out the turning point. The easiest way to work out a turning point, we've done it for quadratics, we do it for cubics as well. When you've got a graphics display calculator, is go menu, analyze graph, and then look for a maximum. And then go either side of your turning point here. Doesn't matter how far to the left and to the right you go. So I'll just click here and click here. And this gives me a maximum of, at x equals 53.3, the maximum is 1.52 e plus 5. And that means move the decimal place 5 times to the right. The plus means right, and 5 is the number of decimal places. So we go 1, 2, that'll be 152. And then 1, 2, 3 more, so it'll be 152,000. Keep that in mind. I'm not going to write it down anywhere. I'm going to explain why in a second. So at x equals 53.3, the volume would be 152,000. Let's go to the answers, and you can see, yep, when x equals approximately 53, and it says Vmax is approximately 151,703. So the fact that we said 152,000 is pretty much bang on for 3 significant figures. But you can see the answers are a little bit better than that. So how can we get a better answer out of our calculator? So all we can do is see this as a written text. But if I go to Control Doc and see it says in blue there plus page, I'm going to add a calculator page. And remember what I've said in previous videos, these pages are all linked. So I've got a value of 53.3 here, and it's stored for function 1. So if I go F1 of of 53.3 and close the bracket and press return, it gives me the more precise answer of 151,703.526. And that is a much closer approximation to the answer in the textbook than what we would have had otherwise. So what would I do? I would go to my, if I was solving this in the calculator section, I would go into here. I would draw the graph for the restricted domain. So just in this section here, oops, that's a terrible graph. Like that. I would label this as 53.3. and 100, I'll have to switch back and have a look. Sorry, I can't remember that. 151,703.5, like so. And in my calculation side, I shall now just go back so you can sort of see what I'm talking about. In my calculations side, I would say by GDC, V max at X equals 53.3, V max equals 151,703.5, and go to 2 decimal places if you want to. And that's basically it. Maybe at this point, put the units in as well because you're finishing off the answer. Okay, hope that makes sense to you. As I said to you before, you can't really work out a maximum without your calculator until you do some differential calculator work. So basically, that's what you need to do. You need to think about the restricted domain. In this case, it's from 0 to 80. Use your GDC to graph the calculator and use the window zoom in order to fit the graph into the window. Use analyze graph to work out the maximum. And then use a calculator page to be more precise with what that maximum would be.